Very good morning to one and all present here. I am here to explain about the one of the adversarial search methodology in AI. Okay, so before going into the method min-max, which is an adversarial search in AI, let me just give an explanation on what is a normal search in AI and what is meant by an adversarial search in AI. So when we just go on for a normal search by using AI, this search will be just going for getting or obtaining a best solution to any problem where we don't have any opponents. There won't be any opponents. Okay. And once it is getting a best solution, okay, the shortest path, cheapest amount, optimal solution, it will just stop, and it is a single agent environment. And this normal search will be based only on the problem constraint. uh, Basically, different types of normal search methodology in AI would be breadth first, depth first, uniform cause search, and so on. Okay, and the main aim of the normal search would be just to reach the target, like shortest, cheapest, optimal solution, and that is the final solution. Okay, now going on to an adversarial search methodology. What is an adversarial search methodology? What is the difference between the normal search, what I just told before, and this one? This adversarial search is basically a multi-agent problem, or it is used in a multi-agent environment. Why? Because this is not the search for the best solution, but this search will be making the best move while we have an intelligent opponent, and we would try to make the move such that we would defeat the opponent. So both us and the opponent will have their best, so that finally they will have a win. Okay, so so how the best move will be anticipated? It is nothing but if I just make a move according to my move, my opponent will make a best move from their end. Okay, okay, so what happened based on both the AI moves, the opponent possibly moves, and ultimately they would have the game to be won. Okay, or maximize the chance of winning depending upon the player. One will have a maximized chance of winning. And several methodologies that are being used in adversarial search are min max, alpha beta pruning. These are some of the methods. Okay, now we have told what is an adversarial search, and this adversarial search is an multi-agent problem, and it is used when an opponent, okay, is there, and the decision of us will depend upon what is the opponent move. Okay, so that is what. So how this works is, we as AI and me as an opponent, AI choose a move, opponent choose the best counter move, then the previous AI will be predicting the future move, continuous until the game ends. Okay, so this is what would be just happening in your adversarial search. Okay, and basically where in what kind of games and all this adversarial search will be used: chess, then multiplayer, any AI game. Okay, then cyber attack, defense simulations. These are some of the applications where we just use the adversarial search. So basically, when I want to differentiate the normal search and adversarial search, normal search is one which finds the best path, and adversarial search finds the best move against the opponent. Okay, so that's how I have just also told about what is the needs. Now, as I just told you, there are different types of adversarial search. One kind of adversarial search is a min-max algorithm adversarial search problem. Next one is alpha beta proving and so on. And this video session, we would just go on with min-max algorithm. So what is a min-max algorithm? A min-max algorithm is a backtracking algorithm, a recursive algorithm. Okay, so which makes the decision making, okay, which is used to have the decision making and the game theory to be got implemented. Okay, so basically in min-max we have two players. One is a minimizer, another one is a maximizer. So maximizer opponent is minimizer, minimizer opponent is maximizer. So how this works on is, the maximizer would be just trying to get the highest score possible, where the minimizer aims on the opposite, that is the lowest score. And every board state has a value which is associated with them, right? So if the suppose if in the board state, if the minimizer is having the upper hand, it will have some negative value. So if the maximizer is having the upper hand, it will have a positive value. So finally, the values of the board would be just calculated by some heuristic methodology for every type of game. So basically, as I just told in a min-max problem, you should have an opponent. Okay. So and it would be applied with respect to a DFS method, what we have seen in terms of normal search AI methodology. It means that we have to go all the way through the leaves to reach the terminal node. So that's what. So from the terminal node, we will have backtracking with respect to the minimizer and maximizer play, and ultimately we'll just reach the initial start point. Okay, so basically when we just see with respect to the working, will players are minimizer, maximizer, and they have the move in a state. Minimizer will have a negative move, and maximizer will have a positive value. Okay, action, they return the set of legal moves in a state. Okay, and what is the result? Result would be the transition model, which defines the result of any move by a minimizer or a maximizer. Okay, so uh, so uh, that is what is your work. Let me just briefly explain how min-max algorithm works out. I've just given you a sample diagram. Okay, so in this sample diagram, if you just see, you have been given with the tree diagram, which has the square shaped which is indicating the maximizer, and the round shape is indicating the minimizer, and there are some values given as W, D and L, where W stands for win, that is +1, and L stands for lose, losing the game, loss, and it is -1, and D stands for draw, it is 0. So actually, minimizer would just go on for the minimum value out of the given. Maximizer would just select the maximum value of the given. So we have to start from the terminal node. So let me just go on with the terminal node. Okay, so and we have to start from the left corner, okay, of backtracking. So if you just go on for the left corner of the backtracking, if you just see here, you have L and D. L stands for -1 and D stands for +1, and square is maximizer, where that has to give the, out of these L and D, it has to give a minimum value. Okay, so out of L and D, if we just go on for the minimum value, L is -1 and D is 0. So -1 would be just given over here. So this becomes LDL. Okay, now it goes on for LLD. Okay, so out of this LLD, okay, it has to give a value to the next maximizer. The maximizer has to select the maximum value out of this LLD. So maximum value out of the LLD would be nothing but L stands for -1, D stands for 0. So D would be the maximum. So D is going here. Okay. Now, once this is over, now this next minimizer has to select depending upon what is been branched. So we will just go on for the next stage of this L and D, right? So next is this L and D has to give a value over here. Okay. So uh, has to, this L and D has to give a value over here. So out of this L and D, that is a maximizer, has to give a value of a minimized value. So out of L and D, L is the minimized value, so L goes over here. Then LWD is the minimizer value, where out of this minimized value, maximizer has to choose the maximum. So W would be just chosen here. So obviously here already W was existing and we already played with the D over here and we have made another one W over here. So now when we want to select the minimizer out of D, W, 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 D is the minimum value. So D goes over here out of this D and W. Now W is the single branch, so the minimizer has to only select W. And while just going on for the next branch, because you know that this min-max algorithm starts with the terminal, reaches the initial. So out of this L and D, okay, a minimum value that has to be played is L, because L is -1. Then out of L, D and L, I have to give a maximum value. So D is 0, where L and L is -1. So maximum value D goes over here. So ultimately when I just go over here, only W is branched to this minimizer, so W goes over here, and D is branched to this minimizer, so D goes over here. So ultimately I have got DWD. So out of this DWD minimized value, this maximizer has to choose the maximum out of this DWD. D is 0, W is 1. So out of the zeros and 1, 1 is the maximum. So ultimately, the min-max problem has given W to be the initial state, that is the win point. Okay. So likewise, we can just go on for doing the adversarial search from the bottom end, that is the terminal node, as a recursive or backtracking methodology, right? So here I've just given you a sample problem with constant values such as -1, 4, 2, 6, -3, -5, 0, 7. So ultimately how this is going on for the terminal node is given. I have to find what is the maximizer for the win of this game. Okay, so obviously -1, 4. Okay, so this is a maximizer, this is a minimizer, this is a maximizer, and this is a minimizer. So this maximizer has to select the maximum value out of -1 and 4. It has to start from the left corner. So out of -1 and 4, the maximum value would be 4 over here. Out of 2 and 6, maximum value will be 6 over here. Out of -3 and -5, the maximum value is -3 over here. 0 and 7, the maximum value will be 7 over here. Okay, so after this out of 4 and 6, a minimum value has to be chosen, and ultimately 4 comes to be, and -3 and 7, a minimum value has to be chosen, and that is -3 comes to there. So after that, 4 and -3, a maximum value has to be chosen, so 4 goes over here. Now what is the best solution is this: 4, A, B, D and I. So that is the solution for your min-max